Hello, it's me. So this is a video about the introduction to differentiation, which is what we're studying tomorrow. And I just wanted to give you a bit of an intro to my intro before we started. So one curve that we are, I hope, incredibly familiar with is the line. So, for example, let's just look at this line here, right? And we can say quite a lot of things about this line. We can talk about the y-intercept. We can talk about, distances, midpoints, all this kind of stuff. We know a lot of things about the coordinate geometry on the number plane. The thing that we know about this one that's most important right now is its slope, right? And the slope is the same as the rise over the run. And you've probably heard the word gradient used before. So, if you go walking up a hill, they'll often, and you look at a guidebook for going for the walk, they'll often talk about the gradient of the slope, the gradient of the hill. Gradient and slope in maths mean the same thing, by the way. But basically the gradient is the rate of change. Oh dear, I tried to go a two-finger there, didn't work. So rate of change. Right, so remember, talk as a scientist, because I am a scientist, x is an independent variable, so as x changes in a constant manner, positively, what happens to y? So that is the rate of change. So if you take one lesson from this video, it is that the gradient is the rate of change. Right? So rise over run, in this context, we know all about. And the thing about this line that makes it nice is it doesn't matter where I draw a triangle. It doesn't even matter the scale of the triangle, right? Effectively because of trig. We know that all these triangles that I'm drawing now will have the same ratio of rise over run. Tan theta is the line, the slope, blah, 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 blah. There's a lot of different ways we know about this. So, what happens when I have, instead of a line, what happens when I have a curve? So what happens when I have like a parabola? Alright, so there's a parabola. Let's pretend I hit the origin and let's make it y equals x squared, roughly. So what can we say about the gradient of this curve? So that is the slope, that is the rate of change. So let's look just like in this region here that I'm highlighting now, and I'll rub out in a second. So what can we say about the rate of change? So we can say that as I move from here to here on the x, I go up about that far. So maybe the slope there might be like 2 or something, So, and that tells me that over this region, the average slope of the curve is 2. Now, if you look at it, and I'll get rid of all this stuff, if I was a bit better at drawing and it was a bit smoother, you'd see that this section here is not quite as steep as this section here, right? A parabola goes, like this. It's flat here, gets steeper, steeper still, and it keeps getting steeper as it goes on. So the rate of change is actually changing, right? So on average, over this region, the rate of change might be about 2. As I go across 1, I go up 2, whatever that scale is. But in different sections, it's changing. So maybe at the end, maybe here the slope is like 3, and here the slope is, 1. And so what differentiation does is it tells us exactly the slope at these points. And it does that by drawing these things called tangents. A tangent, in the first red circle, if I attempt to draw a tangent, I'll probably fail dismally. Look at me being positive about myself. Jeez. I'm sure I'm going to give it my best effort and it's going to be good enough. So if I draw a tangent, go away. If I draw a tangent there, so you can see it just touches the curve there, but doesn't pass through. And the idea is we define the gradient of the curve at this particular x value, whatever that is, x1, we define the gradient of the curve as the gradient of this tangent. Right. And there's a particular notation that we'll get to later, which is dy dx. We might not even get to that today. Okay. And so you can see that tangent there has some slope, maybe it's 1, And if I draw another tangent at the second point, you can see, pretend I was a better drawer, but you can see it's a steeper line. And so the point is that as we move across the curve, the gradient changes because the tangents change. If I draw a tangent here, it has slope 0. We call that a stationary point because the curve is stationary. Right? In this particular instant, when x is 0, the curve is not going up or down, it's flat. Over here, the slope is negative. If I draw a tangent, the curve is going down. As it goes across, the curve is going down. You're walking downhill. So, the last thing I want to talk about is how do you draw a gradient curve. So again, let's just pretend I've got a parabola. So here's my parabola, and I want to draw a curve that represents the gradient for all values of x. So if I move along the curve, I'm going to mark out the gradients. So here, the gradient is 0, right? At x equals 0, the gradient is 0, because it's flat. As I move across here, the gradient is positive, and we also know it's getting bigger as we go on. As we move back here, the gradient is negative, and we know it's getting steeper, which means a bigger negative number as we go left. So then the gradient curve must satisfy those things. So firstly, it must be 0 when x equals 0, so it must pass through that point here. As we go to the right, it must be positive and get more positive, something like that. As we go to the left, it must be negative and get more negative, something like that. So for a parabola, the gradient is a line. Okay? We will extend on that idea tomorrow. I would encourage you, have a go at x cubed. What is the gradient? Okay? Have a go at x. What does the gradient look like? Have a go at x to the power 4, but do a curve like this. Do the W style of x to the power 4. And think about what the gradient curves look like. Okay? I look forward to seeing you tomorrow morning. Until then.